and share your screen. So second presentation will be given by Ivan Vartaniants, and he's also from DESY. And the topic is also very similar, focusing on a little bit different material or nanoparticles. So spatially resolved X-ray, nanodiffraction, and fluorescence of caesium, lead, halide, perovskite, supercrystals reveals quasi-atomic behavior of nanocrystals. So we see your presentation, so please then go ahead.
Thank you, Max, very much for your kind words. And so it's my pleasure to give this talk. And so this is a very nice time also for this talk, because the paper was just accepted in Nature Communications, and who will be interested, he could find also the preprint on arXiv. And it's important to point out that this collaboration between two groups in Tübingen, Markus Schily and Frank Schreiber group, and our group in at DESY. So what we were interested in this particular work about analogy between atoms in crystals and nanocrystals in supercrystals. And supercrystals, or also mesocrystals, as Nastasia already talked about, are an ordered structure of nanocrystals with mesoscopic size. And the nanocrystals in such superstructures are typically mutually oriented and approach the structural precision of atomic single crystals. And you could see here some examples of that. And also, if you are interested, you could go to this review papers. And why it is interest to these systems, because they have a huge applications at the moment, and potential for some applications. They have self-assembly, they have unique mechanical properties, they have interesting electronic properties for the photoluminescence, they possess ligand exchange, and they have interesting electronic properties, especially for conductivity. And as Nastya already said, so this structured transport properties were studied by us also, and you could, hopefully you have visited the 26th poster on this meeting. So what we studied in this work, it was a very specific nanocrystals. So it was so-called caesium, lead, halide, perovskite supercrystals. So, and in the laser light, they have the different color, and so that's why one of them is blue, like here, and one of them is green, like here. And so this is nanocube size is about 7 nanometers, and they're self-assembled into supercrystals on a Kapton film. That was done specially for X-ray measurements. And the supercrystals are of few micron in size, as we talked already. Why were we interested specifically in this materials? Because it is some evidence that there is superfluorescence observed on this lead halide perovskite quantum dot superlattices, and this was studied by Henry Brown and this experiment with visible light, and this is of course quite interesting. And our question was, how does structural disorder affect the quantum coupling of the nanocrystals? And to answer this question, first of all, we studied optically spectroscopy was made, so optical measurements were performed by inverted confocal laser scanning microscope with 405 nanometer laser as the excitation source, and lateral resolution at that source was 200 nanometers. And approaching NH of the supercrystal, we observed a blue shift, as you can see here, for both crystals. And it was 220 MeV for this sample and 12 MeV for this sample. Also, it was interesting to study a lifetime, and so for this system, typical fluorescence lifetime is 2.2 nanoseconds in descent, and it decreases by 20% when you approach edges. And for the green sample, typical fluorescence time was 1.5 nanoseconds in the center, but it decreases by 30% when it approaching edges. And to perform X-ray studies, we made very similar experiment like Nastasia has shown just, and we used, so first of all, we performed measurements at PCAM beamline at Petra 3 source, and we use specific Ginix end station. So we measured at energy at 13.8 keV, and what was important for these measurements that the focal size was 400 by 400 nanometers. So detector, it was Eiger detector. Sample to detector distance was quite short, 400 millimeters. And special scans were made with a step size of 500 nanometers. And what was important for that measurements that we specially shifted detector that we could simultaneously measure SAX pattern together with the VAX pattern, and that was very important for us. Okay, first of all, average structure. First of all, if you look on this result, so it is SAX-based diffraction map, and so you can easily see a single isolated supercrystal about with the size of 7 microns, and IFM measurements give thickness of few hundred nanometers for these supercrystals. So if you look on average VAX pattern, then you can say already that the observed peaks can be attributed to simple cubic lattice with unit cell parameter of 0.5 nanometers arranged along 001 atomic lattice. And from the Williamson-Hall analysis, the broadening gives us nanocrystal size about 6.8 nanometers, and the atomic lattice distortion that is about 2.8%. And if we look on the SAX pattern, then we see that cubic nanocrystals were arranged also in a simple cubic lattice. And peak positions gives us the unit cell parameter that is about 9.9 nanometers. And interparticle separation is about 3.1 nanometers. So then we look a little bit more closer to the SAX analysis, and we performed scanning now. So we don't look on just one point, but we look on the whole structure, not on the average, but on the structure. And so what we saw, that local super lattice structure is rather monoclinic, and lattice anisotropically shrinks from the middle towards the edges, as you can see from this B slide. Then mean unit cell parameter changes from 10 nanometers in the center down to 8 nanometers. So here you can see it. Lattice preferably shrinks in the direction parallel to the nearest edges, and angle pointing to the nearest corners is abused. And explanation is that surface tension of the solvent during self-assembly is leading to a smallest perimeter as possible. Then from the VAX analysis, we could say that the following, that mutual orientation of 100 superlattice and 010 superlattice cannot be maintained. The angle between them is not angle exactly to 90 degrees. The angle between 010 atomic lattice axis and the mean line M remains constant within supercrystal. And again, from the Williamson-Hall analysis of the azimuthal now for width half maximum of the VAX black peaks, we found that angular disorder increased from 10 degrees in the middle and to 24 degrees at the edges. And then we could say very importantly about the local atomic structure. So local unit cell parameter of the atomic lattice from the cube position of the wax peaks stay quite stable, as you could see here. But the local strain obtained from the Williamson Hall analysis grows to the edges. So you see this decrease, and that's the growth of the local strain. Okay, so I'm coming to conclusions. So supercrystals of lead, halide, perovskite, nanocrystals exhibit a loss in structural coherence and increasing atomic misalignment between the adjacent nanocrystals and compressive strain near the surfaces. And importantly, the structural distortions are strongly correlated with the blue shifted fluorescence and decreased radiative lifetimes. So that's our group, and also thanks to everybody who performed these measurements, and especially to P10 Beamline and Michael Sprung there. And thank you for your attention.